So this is the third lecture of gravitation. Okay. One more thing. At the end of lecture, I'll give you some common things or common questions. Okay, from JW Advanced, and how to solve them. How to solve them means, see, if you use irodov as a standard books, okay, it is more or less complete information or complete portion of your syllabus. Okay. So which portion of the question or which question is relatable to what questions in irodov? I'll give the similarity between irodov and the questions that have been asked in JW Advanced. Okay, at the end of the video on the chapter of gravitation. Okay. So let's start our lecture. So you are at question number 213. Okay. In this question, okay, so the question out here is there is a hemisphere. Okay. I've drawn a table hemisphere out here. There is a hemisphere. The mass of this hemisphere is m. Okay. Now there is another mass, small m. The question is asking what is the work done against gravitational force in bringing this point mass m from this point to infinity. Okay. To understand or to solve this problem, you must first understand the concept of principle of superposition. Okay. Principle of superposition. This thing I have already done in your electrostatics. I'll do it again. Okay. What principle of superposition says that suppose I'm finding out field, okay, or force on 1 kg of mass. Okay. Now this force on or gravitational force due on this 1 kg of mass would be due to some other masses. Okay. Suppose there was some other mass m1, and the gravitational force due to m1 is nothing but g m1 by r square, where r is the distance between this point and this point. Okay. My question out here is if there is another mass m2 out here. Okay. Now what is the total gravitational force out here? What principle of superposition says that the total force in this 1 kg block or the total field at this point in space is nothing but individual vector summation of all the gravitational forces. That means the gravitational force due to this m1 would be g m1 by r square. The gravitational force due to this m2 would be g m2 by r square, isn't it? G m2 by r square or r2 square, where r2 is the distance between this point and this point. Okay. If there is third particle, gm3 by r3 square. If there is fourth particle, gm4 by r4 square. So total field or total field at a point in space is nothing but summation or vector summation, okay, of all individual field. Individual field. Okay. Similarly, the total potential at this point in space, okay, or total potential energy of this 1 kg block. Total potential is equals to scalar summation of all individual potential. That means what? That means if I want to find out the total potential and this 1 kg of block, it is nothing but potential due to this block plus potential due to this block plus potential due to any other block m3 block plus potential due to m4 block and so on. If I'm finding out the total field is nothing but vector summation of force or field due to this block plus field due to this block plus field due to third block plus field due to fourth block. And if total potential is asked, the total potential at this 1 kg block is nothing but potential due to this m1 block plus potential due to this m2 block plus potential due to m3 block and so on. Okay, fair enough. Now using this concept or using the principle of superposition, how do I solve this one? Okay, what is the relation between principle of superposition and this question? Okay. The hemisphere out here is a little bit tough to solve. Okay, so instead of solving for hemisphere, I'll solve for entirety of sphere. Okay, so what I'm doing out here is there was already a sphere of mass m, capital M. Okay, and a small mass m was kept out here. Now what I'm doing is I'm creating another mass m. Okay, I'm creating another mass m. I'm making this entire shape a sphere. Okay, why did you do that? Because I know the total work done or I know the potential energy of the small mass m at the center due to a complete sphere. Okay, that I have already derived. And using the principle of superposition from the complete sphere, I'll derive the hemisphere. So what I did right now was I created another hemisphere and made this into a total sphere. Okay, so for total sphere, the question is asking what is the work done in bringing this m mass from this point to infinity. It is nothing but potential at this point. The definition of potential is only that, no, work done in bringing a unit charge or unit mass from infinity to that point, or work done against a gravitational force from infinity to that point. Okay, that is the definition of potential. Okay, so the potential energy of 1 kg of block at the center of the total sphere would be nothing but, we have already read this one, it is nothing but u is equals to minus gm by 2 or 3 minus x square by r square. So let's copy this one. Okay, so u is equals to how much? This is the potential at the center of a solid sphere. Fair enough. Now the x out here is nothing but the distance from the center. So if I'm finding out the potential at the center, what is the value of x? The value of x is nothing but 0. Why? Because I'm finding out the potential at the center. So potential at the center is nothing but gm by 2r into 3. But if I rewrite this neatly, it is nothing but minus 3 by 2 gm by r minus 3 by 2 g into m by r. But m was the mass of the sphere. Okay, do not get confused between this variable and this m and n. M was the mass of the sphere. What is the total mass of the sphere out here? The total mass of the sphere out here is nothing but m plus m, isn't it? M plus I created another sphere of similar mass m. So total mass is nothing but 2m. One more thing. The potential that I found out here was for 1 kg of block, no? But I need to find out the potential energy of m kg of block. So potential energy of m kg of block is nothing but potential energy of m kg of block is nothing but m into u, isn't it? Or mass into potential. Okay. So potential energy is nothing but minus 3 by 2 g into 2m by r into m. So all of you have understood up to this point. Okay, first what I did was I found out the potential at the center due to a complete sphere. Okay, potential at the center is given by this formula. In this formula, mass was nothing but the mass of the sphere. In our case, mass of the sphere is nothing but m plus m is equals to 2m. Okay, now this potential, the formula for potential that is derived, is for 1 kg of block. Field and potential are nothing but defined for 1 kg. Okay, fields and potential are defined for 1 kg or 1 coulomb in electrostatics or 1 unit of magnetism in magnetic or magnetism. Okay, so field is nothing but force on 1 kg of block, potential is nothing but potential energy of 1 kg of block. Okay, fields and potential are defined for unit things or unit quantities. Okay, so out here potential at the center is nothing but 3 by 2 g into mass of the sphere divided by r. Okay, so the potential energy of m kg of block is nothing but potential of 1 kg of block into m, isn't it? This is nothing but the potential of 1 kg of block into m. So I found out the potential of m kg of block. Understood? So potential energy of m kg of block is nothing but, let's cancel out the 2 out here, is equals to 3 gmm by r or minus 3 gmm by r minus 3 gmm by r. This much is understood. Okay. The question is asking what work was performed in the process by gravitational forces exerted by the hemisphere. Okay. See, a particle of mass m was transferred from the center of the base of a uniform hemisphere of mass m and radius r into infinity. That means from this point, the particle is going to infinity. That means it is nothing but work done against a gravitational force from infinity to this point. Both are the same thing, no? Okay. Understood. So, see, in moving this mass m from this point to infinity, I have to apply some amount of work because gravitational forces is always trying to attract the mass m. Okay. So external force is nothing but positive. Okay. That means work done. So potential is negative. Potential is negative. Work done is nothing but negative of potential energy. Why? Because I have to do some work in bringing this mass m from this point to infinity. And the amount of work I have to do is nothing but exactly the potential that is at the center. So work done is equals to 3 g capital M small m by r. Okay. So work done in bringing a small mass m from this point to infinity is nothing but this parameter. Fair enough. But the original question was asking for hemisphere. Okay. Now listen to me carefully. Okay. If I divide this two sphere, listen to me very carefully. Okay. Suppose this sphere, I copied it. Okay. Let me just copy this one. This sphere. Okay. I'll just erase out. Now this sphere. Okay. This formula is obtained for this sphere, no? So if I just separate out this sphere, capital M mass, and small m mass. Now seeing the thing or seeing this diagram, can I say work done by top part of the hemisphere in moving this block is equals to work done by bottom part of the hemisphere due to symmetry? Because the top part and bottom part are symmetrical, suppose I'm moving this mass m, okay, like this to infinity. So work done against upper portion of the hemisphere is equals to work done against lower portion of the hemisphere. So from symmetry, work done by top hemisphere is equals to work done by bottom hemisphere. Okay, HSP is nothing but hemisphere. So work done by top hemisphere is equals to work done against bottom hemisphere. Sorry, work done by top hemisphere is equals to work done by bottom hemisphere, isn't it? Because they are symmetrical in nature. Okay, and I'm moving this particle from this point to infinity. Fair enough. So if I say work done against, or let work done by top hemisphere or work done against top hemisphere is equals to x. Top hemisphere. Okay, THSP is nothing but top hemisphere. So work done by top hemisphere is equals to x. Okay, so by symmetry, work done by bottom hemisphere is also x. Okay, and is there any other masses out here apart from top hemisphere and bottom hemisphere? No. So the total work done is nothing but x plus x. And what is the total work done? Total work done is nothing but 3gmm by r is equals to 3gmm by r. If I solve this equation, 2x is equals to 3gmm by r and x is equals to 3 by 2 g capital M small m by r. Okay, so these are the answer. Next part of the question. This part of the question we already have done before. Okay, in this question it is asking there is a solid sphere. Okay, of mass m. There is a solid sphere of mass m and radius r. Okay, find out the strength of gravitational field and potential from infinity to center of the sphere. That means what the question is asking is there is a sphere out here. Okay, draw a graph. Graph means a 2D graph. And in this graph, okay, draw actually not one graph, draw two graphs. Okay, and in this graph, on the x-axis, there should be distance from the center. On both these graphs, there should be distance x from the or distance from the center. Okay, that means at this point, at r is equals to 0 at the center of the sphere, at r is equals to capital R at the surface of the sphere, at r is equals to infinity from distance infinity to the sphere. Okay, so there are two graphs, and you have known what the x part of the graph determines. Okay, now the question is asking for the first part of the graph, the y-axis should be filled. That means in graph 1, okay, there are two graphs. In graph 1 or plot 1, okay, it is field versus distance from the center. Okay, whereas for graph 2, it is potential versus distance from the center. Potential versus distance from the center. I have already done this question, but in a little bit different manner. Okay, see out here. Okay, what was the for a spherical ball of mass m or a spherical planet of mass m? Okay, there are three cases: outside the sphere, on the surface of the sphere, inside the sphere. Okay, so this is the thing that I must refer to turn and again. Okay, again and again out here. Okay, now let's divide this graph into three categories. Okay, this is the surface of the sphere. That means out here is my radius r. Okay, this is radius r. This is radius r. Okay, any point outside this r or any point outside this r, okay, or outside the sphere will be categorized as outside the sphere. And what is the formula for gravitational field outside the sphere? Minus g m by r square. So for outside the sphere, the formula for gravitational field is g is equals to minus gm by r square, where r is the distance from the center. Fair and fine. So out here at the surface, okay, what is the gravitational field? Minus gm by capital R square. Okay, so it would be some, let's say, value. Okay, one more thing, you might say, sir, it is written as minus, but you are showing in positive y-axis. Why is that? Out here, I'm just considering the magnitude, not the summation. Okay, or not the sign of the vectors. Okay, right now I'm just considering the magnitude. Okay, only the magnitude of the thing is considered. Okay, so out here, okay, out here, gm by r square, isn't it, at the surface? So potential at the surface is equal to nothing but gm by capital R square. Now, as I increase the value of r, okay, how would a graph of g is directly proportional to 1 by r square look like? The graph would somewhat look like this one, isn't it? This would be the graph. Okay. Similarly, what is the potential at surface or potential outside the sphere? The potential outside the sphere, okay, potential outside the sphere is nothing but minus gm by r, isn't it? So potential outside the sphere is nothing but minus Gm by R. Okay. Even out here, I'm just considering the magnitude. So potential is nothing but minus Gm by R. I'm just considering the magnitude. Okay. Or potential is equals to Gm by R. Okay. You can either write potential as E or psi. It doesn't make a difference. Okay. Potential is equals to minus Gm by R. At the surface, what is the potential? Gm by R. Okay. At the surface, the value of potential is nothing but Gm by R. And as I increase the value of R, what will happen? The graph will look somewhat like this. Potential is directly proportional to 1 by R because G into M is already a constant, no? So potential is directly proportional to 1 by R. So it would look somewhat like this. Okay. So out here, okay, on the field graph, my equation is G is directly proportional to 1 by R square. On the potential graph, potential is directly proportional to 1 by R. As I increase the value of R, the value of potential and the value of field decreases. Okay. And at the surface, what is the value? The value is Gm by capital R. The value is Gm by capital R, and the value of field is nothing but Gm by capital R square. Fair enough. So there are two cases I have done. Okay. Now, what is the potential inside the sphere, or potential and field inside the sphere? So let's look at this formula. Okay. I'm considering about the third case, potential and field inside the sphere. Okay. So let's go back. Okay. Out here, point inside the sphere. Okay. G mass inside by R square. So what was the formula that I derived? F is equals to, or field inside the sphere is nothing but G into M into X by R cube. Okay. Inside the sphere, field is nothing but G mx by R cube inside. Okay. The first part is outside, the same part is inside. G is equals to G mx by capital R cube. Now this G, M and capital R is a constant. Capital R is nothing but the radius of the planet, isn't it? So G, M and capital R is constant. So I can directly write G is directly proportional to X, isn't it? So below this point, okay, the graph would look like a straight line. This is a straight line. But the equation is G is directly proportional to R. And the exact equation of the graph is nothing but G is equals to G mx by R cube. Fair and fine. Now similarly, what would the graph of potential look like below or inside the surface of the sphere? The formula out here is nothing but, let's look at the formula. The formula is not this one, not this one, this one. The formula is nothing but Gm by 2R, 3 minus x square by R square. Okay. It is nothing but Gm by 2R, 3 minus x square by R square. So potential is Gm by 2R, 3 minus x square by R square. Okay. See out here. I'm just seeing the magnitude. Gm by R, not this one. Gm by 2R, 3 minus x square by R square. Potential inside a sphere. Okay. Now see, one thing. X square is always lesser than R square, because whenever I'm finding this formula, it is only valid for potential inside the sphere. So inside the sphere, the value of x will always be lesser than 1. So x square by R square is always lesser than 1. Okay. So 3 minus something lesser than 1 is always a positive number, isn't it? So as the value of x decreases, now see, okay, as the value of x decreases, okay, what will happen? The potential will rise. Why is that? See, as the value of x decreases, x square by R square will also decrease, isn't it? As the value of x, I'm starting from R, okay. As the value of x decreases, that means as I'm going this side towards the left, okay, the value of x square by R square also decreases. So 3 minus this ratio increases, no? So if this increases, then the potential also increases. If you want to understand it by another method, okay, what is the potential at surface? Potential at surface is nothing but replace this formula by capital R, isn't it? If you replace this formula by capital R, 3 minus capital R square by, so if you replace this formula by capital R, it gives me nothing but Gm by 2R, okay, 3 minus R square by R square. It will be the same formula that we have derived before. 3 minus 1. 3 minus 1 is nothing but 2. Okay. 2 and 2 would get cancelled and it would be Gm by capital R. So potential at surface is nothing but Gm by capital R. Same formula as before. I'm ignoring the minus sign. Okay, I'm just concerned about the magnitude. Out here also minus sign is ignored. So potential at surface is equals to Gm by capital R, same as previous formula. Now, what would be the potential at the center? The potential at the center would be nothing but U is equals to Gm by 2R, 3 minus x square, 0 square by r square. So 0 square by r square is nothing but 0. Or potential at the center is nothing but 3 by 2 gm by 2r. Now just tell me by common sense which is greater, gm by r or 3 by 2 gm by r. 3 by 2 is nothing but 1.5. This is nothing but 1. So obviously potential at the center is higher. Understood? So as I'm going from surface to inside the sphere, the potential keeps on rising. Okay. So the graph would be somewhat like this. Now you might ask, how do you know the shape of the graph? The shape of the graph is nothing but mathematical equation of this equation. So how do you know this equation? This you have to memorize on your own. Okay. There is no standard or generalized. There won't be generalized things out here. But if you study in class 12 parabolas and this is nothing but a form of parabola. Okay, equation of a form of parabola. Okay, that will be taught in class 12. But there is no need to study the entire concept of parabola for this understanding this much. Just memorize the graph. This graph looks like this one. Okay, nothing more, nothing less. Okay. So in this question, okay, out here there is a planet, a spherical planet. Okay, inside this planet there is a cavity. Cavity means nothing but hollow space. Okay, that means all the masses are out there. Okay, there is no mass in the hollow space. We have to find out the gravitational field inside the hollow space. Gravitational field inside hollow space. Okay. One more twist is there in this question is that instead of giving you the mass of this planet, they have given you the density of this planet. Okay. So in terms of density, suppose there is a hollow planet or suppose there is a full planet. Okay, I have to find out the gravitational field inside. What is the formula? The formula is nothing but field is equals to g mass of planet into x divided by r cube, where r is the radius of the planet, isn't it? This is the formula for field inside the planet. Okay. Now suppose instead of giving you the mass, they have given you the density of the planet. Can you find it out? Obviously, we just substitute mass by density because we know that density is equals to mass by volume. So mass is equals to density into volume. This mass is equals to density into volume. And the volume of a sphere is nothing but 4 by 3 pi r cube. 4 by 3 pi r cube. Okay. So volume of this sphere is nothing but 4 by 3 pi r cube. So field inside a planet is nothing but g into rho density of the planet into 4 by 3 pi r cube into x divided by r cube. R cube and r cube would get cancelled. Or f is equals to g into rho into 4 by 3 pi x. What I have simply done out here is I have rewritten this formula in terms of density. This is the same formula as this one. This formula is same as this one, but instead of using the mass, okay, I've used the term of density. Okay, this and this are the same formula. Formula for field inside a planet. Similarly, some additional information. What about the formula F is equals to g m by r square? What about this formula? Same kind of thing will happen. Replace mass by density into 4 by 3 pi capital R cube. Okay, if the field is found out at the surface of the planet, this capital R become or this small r becomes to capital R, isn't it? Okay, so same thing I've done out here. Okay, that means I have written the formula in terms of density instead of mass. So I'll just use this formula because the question out here is given density. Okay, you have to find out in terms of density using instead of mass. Understood? So my main formula for field inside a sphere is nothing but g into rho into 4 by 3 pi x. G into rho into 4 by 3 pi x. Okay. So let me erase this one. Fair and fine. Now, how do I find out the field inside this cavity? Okay. How do I find out the field inside this cavity? See, we have to use a principle of superposition. Principle of superposition means let a point, there be a point inside cavity, or let this be a center inside cavity. This is the center of cavity. Okay. So point or gravitational field inside cavity is equals to gravitational field due to the entire field of sphere at this point at the center of cavity minus gravitational field assuming the cavity was filled with some mass at the center of cavity. This point, the point that I'm drawing out here, is at the center of cavity. Okay, distance from the center of the circle to center of cavity is x. Distance of the center of circle to center of cavity is x. Distance out here is equals to acha. This is since this is the cavity itself, out here distance will be 0. Okay, so if I apply the formula, okay, g total or gravitational field total is equals to g due to complete sphere minus g due to hollowed out sphere, isn't it? This is the principle or superposition principle that I'm applying. Total gravitational field inside the hollow cavity is equals to gravitational field due to an entire field sphere minus gravitational field assuming the hollow space was filled with some mass. Okay. Now we know the formula. What is field inside, or what is field at point 1? Field at point 1 is nothing but, what is the formula? G into 4 by 3 pi x. So G into 4 by 3, not small g, capital G. Capital G is nothing but gravitational constant. G into rho into 4 by 3 pi x, where x is nothing but the distance from center of the sphere, or center of the larger sphere, to center of the cavity. Okay. Minus, what is the gravitational field at the center? If we apply these formulas once out, again out here is nothing but, this is nothing but, or gravitational field out here is nothing but 0. Okay. Gravitational field at the center of the planet is equals to 0. Okay, because if you put the value of x out here, it becomes 0. Okay, so total gravitational field at the center of cavity is nothing but g into rho into 4 by 3 pi x. Okay, where x is the distance from center of sphere to center of cavity. Okay, now note one thing: the direction of gravity field, or the direction of gravitational field, will be in the direction of x. Okay, so if this is x vector, the direction of gravitational field would be this side, or towards the center, isn't it? The direction of gravitational field would be this side, or along the direction of x vector. Now I have a question. I have found out the gravitational field at the center of the cavity. But read the question. There is a spherical cavity whose center is at distance L from the center of the sphere. That means this, the value of x out here, is given as L. Okay. That means instead of using x, you would have used L. Okay, this is the value of L. Instead of using x, I'll use L. Okay. Out here, this is x, this is x. Sorry, L, L. That means I'm using the terms of irodov. Okay. Distance L from the center of the sphere. Fair and fine. Find out the strength G of the gravitational field inside the cavity. So this statement says that you have to find out the gravitational field inside the cavity, not necessarily at the center. I found out the gravitational field at the center, no? So I have to find out the gravitational field inside the cavity, and that anywhere inside the cavity. It cannot, or it doesn't have to be at the center. Okay. So how do I approach that one? Okay. I use the same principle. Okay. But in order to understand this concept, or in order to understand out here, I must draw a larger diagram. Okay. Suppose this one is a cavity. Let's draw a circle. Okay. This one is a cavity. This one is a sphere. Okay. Inside this sphere is another cavity. Okay. This is cavity. Okay. In the first case, what did I do? I found out the potential, not potential. I found out the field at the center of cavity. Okay. So let me say that the distance between center of the planet, okay, center of the planet to center of cavity is given as L vector. L vector. And our gravitational field at the center of cavity is nothing but G into rho into 4 by 3 pi L vector. Fair and fine. Now suppose I want to find out the field out here, okay, at any point inside the planet. Field at point 1. Okay. Due to this complete sphere, okay, due to this complete sphere, okay, due to this complete sphere, what is the field at point 1? What I'm trying to say is, suppose I copy this sphere, okay, I copy this sphere and paste it out here. Paste it out here. I'll just make it smaller. Okay. To drag everything to the left. Okay. Suppose I'm just drawing this sphere a little bit smaller. Okay. Okay. So what is the gravitational field due to the larger sphere? Okay, at point 1. At point 1. It is nothing but, let this point be x1 vector, x1 vector, x1 vector. So gravitational field out here is nothing but G is equals to G into rho into 4 by 3 pi x1. I will use this formula, G into rho into 4 by 3 pi x1. So gravitational field due to larger sphere, okay, at this point, point 1, at point 1, is equals to G into rho into 4 by 3 pi x1. Okay. Now my same question. Okay. What is the field due to the smaller sphere? Okay. Suppose this sphere was filled out with same mass. Okay. What is the field at point 1 due to this smaller mass, or assuming some mass was filled out in this cavity space? So let the center of the sphere be this one. Okay. let this and this one was already 0.1. This one was already 0.1. This is also 0.1. The field at 0.1 due to hollowed out space would be, let's say this vector to be x2. This vector or vector from center of cavity to 0.1 be x2. Vector, this vector is nothing but x2. Okay, from 0.1 to center of gravity. X1 is nothing but from 0.1 to center of sphere. From 0.1 to center of sphere. X2 is nothing but from 0.1 to center of gravity. Okay, what is the gravitational field out here? G2 is nothing but G into rho into 4 by 3 pi x2 vector, isn't it? And this one is nothing but x1 vector. So gravitational field due to complete sphere would be in this direction with this magnitude. Gravitational field, assuming the hollowed out sphere was filled with the same mass, would be nothing but this value, and the direction would be this one. So the total gravitational field at 0.1 due to this entire setup would be this value minus this value, isn't it? This value minus this value. See, principle of superposition. Okay. So total gravitational field is nothing but G1 minus G2, or G into rho into 4 by 3 pi x1 vector minus G into rho into 4 by 3 pi x2 vector, isn't it? Now G into rho into 4 by 3 pi are common in both terms, isn't it? So can I take them common? So if I take them common, what will happen is G into rho into 4 by 3 pi x1 vector minus x2 vector. Okay, this is the value of gravitational field at 0.1. Fair and fine. Now if you observe carefully, x1 vector minus x2 vector is what? L vector, no? See, can I apply triangle law of addition out here? X2 vector plus L is equals to x1 vector, isn't it? X2 vector plus L is equals to x1 vector. From triangle law of addition, can I say x2 vector plus L vector is equals to x1 vector? Or simply, can I say L vector is equals to x1 vector minus x2 vector? So L vector is equals to x1 vector minus x2 vector. So can I substitute this L out here? So gravitational field at 0.1 is equals to G into rho into 4 by 3 pi L. Okay, and L is the center to center distance between cavity and sphere. Now if you observe this formula and the formula that I have obtained before, okay, gravitational field at the center of the cavity is also this value. Gravitational field at 0.1 is also this value. And if you take any other random point inside the cavity, the gravitational field would have the same value. Okay, that means what can I determine? I can determine that the gravitational field inside the cavity, throughout the cavity, at every point in the cavity will remain constant with the value of G is equals to, or gravitational field is equals to G into rho into 4 by 3 pi L. Okay, so what I'm trying to say is gravitational field inside every point in the cavity would be nothing but G into rho into 4 by 3 pi L vector. But L is nothing but center to center distance between center of sphere and center of cavity. Okay, so the gravitational field will look somewhat like this at the center, because at every point in the hollowed out space, the gravitational field is same. Okay, so this is our problem number. Which one? Which problem am I doing? Problem number 215. Okay. Now let's go to the next question. Okay. Now in this question, okay, imagine yourself in a watery planet. Okay, imagine yourself inside Neptune. Okay, the mass of Neptune is m. So what happens when you go inside Neptune? When you go inside Neptune, what will happen? The pressure of water will keep on rising, because what happens? All the water that is above you is pushing down on you. Okay, so as you go inside Neptune, the pressure of water will rise and rise. So this question is asking, find out the pressure at 0.1. Okay, this is 0.1 at distance r from the center. 0.1 at distance r from the center, small r from the center. We have to find out the pressure at Neptune at distance or at 0.1. Okay, because what happens? As you go down and down, all the water that is above you is pushing down on you. Okay, and you have to find out the pressure at 0.1. Okay, okay. One important assumption in this question is that density of the planet is same everywhere. Density is constant everywhere. Everywhere. That means density of water out here is equal to density of water out here is equal to density of water out here, and so on. Okay. There's a side question you might have, so what happens about gaseous planet, or what happens like planet like Jupiter? Okay. If you understand this question, or if you understand how to solve this one, you can understand even that also. Okay, both have similar kind of approach. There's nothing different. Okay, but let's just assume the density of the planet or density of the water everywhere is constant. Okay. Now, if you just learned a little bit of fluid mechanics, okay, in fluid mechanics, what is pressure? Suppose there is a beaker kept out here, okay, and you have to find out the pressure at this point, okay. Or height of the beaker was h, water was filled to the top in the beaker. You have to find out the pressure at this point, okay. Pressure was equals to rho gh, isn't it? And how did I obtain this formula rho gh? Pressure is nothing but normal reaction force divided by area, isn't it? Pressure is equals to normal reaction force divided by area. Okay. So pressure out here is nothing but normal reaction force on this plate divided by area. Okay. Pressure out here is nothing but normal reaction force divided by cross-sectional area of the plate. Okay. And what is the normal reaction force? Normal reaction force is nothing but the weight of the water above the plate or weight of the water above it divided by area. So pressure is equals to normal reaction force divided by area. But normal reaction force is nothing but weight of the water above it. Water above it. Understood this much? What is the weight of water above it? Mass into G, which is equals to mass into G. So pressure is equals to nothing but m into G divided by A. But m into G is nothing but weight of the water above the planet, or sorry, weight of the water above the beaker, isn't it? Above the bottom of the beaker, isn't it? Just forget gravitation for a while. I'm just giving you the basics of pressure. In fluid mechanics, we'll learn that pressure is equals to rho gh. And where does this rho gh come from? Pressure is nothing but normal reaction force acting on the bottom of the beaker divided by area. Normal reaction force is nothing but weight of the water above it divided by cross-sectional area of the beaker. Okay. Well, weight of the water is nothing but mass of water above it into G. What is mass of water? Mass of water above this plate is nothing but density of water into volume. Mass of water is nothing but density of water into volume. And volume of this much amount of water is nothing but cross-sectional area of the beaker. That means how much area of the beaker into height. Volume of this much amount of water is nothing but cross-sectional area into height. So volume of this much amount of water is nothing but cross-sectional area into height. So pressure at the bottom of the beaker is nothing but rho A H G divided by A. And A and A will get cancelled and pressure is equals to rho GH. So this is the way by which you find pressure at bottom of the surface of water. Okay, this was fluid mechanics. But problem out here is in gravitation, the value of G is not constant. Okay, the density of water throughout the planet is constant. But at this point, the value of G would be different. At this point, the value of G would be different. At this point, the value of G would be different. At this point, the value of G would be different. Isn't it? So how do I find out the pressure at this point, at point 1? Point 1, the pressure at point 1 is nothing but weight of water above it divided by area, cross-sectional area. So in order to solve this problem, let's divide this planet into multiple layers. Okay, I've just divided into this much amount of layers, but imagine it to be infinite number of layers. Okay, and you have to find out pressure at point 1. Pressure at point 1. Okay, which is at distance r from the center, smaller from the center. Okay. Now, if you see properly, or if I just take this much amount of study one, okay, you can take the entire planet also. You can take this much amount also. It doesn't matter. It doesn't matter. Okay, just understand with this much. The same can be applied for entire thing. Okay. What is pressure at point 1? Pressure at point 1 is nothing but normal reaction force divided by area. Or pressure at point 1 is nothing but weight of water above point 1. Weight of water above point 1 divided by this much amount of area. Understood? Weight of water above point 1 divided by this much amount of area. Okay. Now assume, okay, I laid out this in a flat plane, or I made this circular or spherical part into flat rectangular part. That means I just flattened out every part or every layer. That layer would look somewhat like this, isn't it? Okay. Suppose I want to find out the pressure at point 1. Pressure at point 1 is nothing but this is R. It is nothing but weight of the water above it. Weight of the water above it divided by cross-sectional area, divided by area of this much amount of plate, isn't it? Weight of the water above it divided by area of this much amount of plate. This much is understood. Okay. So it is nothing but weight of water above it divided by area. Weight is nothing but m into G divided by area. Okay. Problem out here is G is not constant. Okay. M is nothing but mass of water above this much amount of area. I have to take only this much amount of mass. Okay, so how do I take this much amount of mass? This much amount of mass is nothing but density of this water into area into this much amount of height, isn't it? So pressure is nothing but density of this much amount of water into area into height, isn't it? Mass is nothing but density into volume. Okay, volume is nothing but area into height. Let me again break this down. Okay, mass of water above 0.1 is nothing but density into volume. Okay, mass of water out here is nothing but density into volume into G divided by A, density to volume of this much amount of thing only, or this much amount of water only. Okay, I'm not taking the entire volume of the planet. Okay, volume of this much amount of water, because pressure will be applied by this much amount of water. Okay, now let's separate this one. Okay, pressure is equals to rho, density is constant, into G V by. Now my question is, what is volume? Volume is nothing but area, this much amount of area or cross-sectional area out here, or cross-sectional area of this plate into height h. Volume is nothing but area into height h. Okay, fair and fine. Out here I have a little bit of problem. If I use area into height h, or if I take the total volume, what will happen is, see, at this rate, okay, at this point in the planet, gravitational force is different. At this point in the planet, gravitational force is different. At this point in the planet, gravitational force is different. So if I multiply this entire A into H, so if I multiply this entire volume by this value of G, or value of G out here, I'll get an average error, no? I'll get an average result that won't be accurate. Okay. So how do I do this? I take an element dx, okay, or dr, and integrate that element dr from this point to this point. Okay. Instead of writing h, I have integrated, or I have taken integral of element dr from this point to this point. Okay. Or let's name this, instead of using variable r, let's name this x. Okay. Rho g, instead of using r, I'll use or dx. Okay. Understood this much? Okay. Instead of using h, I have used integral of dx from x is equals to h. The lower limit is nothing but x, or this point. Okay. The upper limit is nothing but radius of the planet. Okay. So our pressure out here is nothing but rho g a into x r dx divided by a. Okay. A and a would get cancelled, or p is equals to rho g r x dx. Okay. Fair and fine. Now, why did I take the h, value of h? Because gravitational field at every layer would be different. So out here I have to manipulate, or I have to modify this value g also, no? Because gravitational field is not constant, isn't it? The value of g, or gravitational field, is nothing but g into mass inside divided by r cube or x cube. What is the gravitational field at point 1? Gravitational field at point 1 is nothing but the pulling force due to this entire mass inside this point 1, isn't it? This mass, point 1, would pull the planet towards itself. So the value of g out here is nothing but g, gravitational constant, into mass inside divided by x square, isn't it? Divided by x square, that I have already told you before. And if I modify this formula, or if I solve this formula, it is nothing but g into mass into x divided by capital R cube, where g is nothing but gravitational constant, m is nothing but mass of the entire planet, x is nothing but height at which I have to find out the gravitational field, divided by r cube. R is nothing but radius of the entire planet. Understood? So the pressure out here, okay, let me solve this one. So the pressure out here, okay, let me just erase some part. Okay, so the pressure out here is nothing but rho into this value into this value. So rho into gmx divided by r cube into dx, and x from how much? X to capital R, isn't it? Now what are the variables out here? Only x and dx. So if I integrate this one, pressure out here is equals to rho g m by r cube into x dx, from x is equals to r. Okay, distance r, okay, from x is equals to r to capital R. Or p is equals to rho g m divided by r cube into x square by 2. Okay, from x is equals to r to capital R. So pressure is equals to rho g m divided by r cube into r square by 2 minus r square small r square by 2. Okay, I have a problem. Okay, not problem. This is the final answer, but I want to make this answer a little bit neat and clean. Okay, what was rho? Rho was nothing but density of the entire planet or density of water. Now, problem is, can I substitute this density in terms of mass? Obviously, density is equals to mass by volume or mass of the entire planet divided by volume of the entire planet. Okay, so I'm just substituting density by mass. So mass is equals to density into 4 by 3 pi r cube. Okay, I'm just substituting the value of rho out here. Okay, so rho is equals to mass by volume. Okay, rho is equals to mass by volume or pressure. Let me raise the bottom part also. Okay, I'm raising the bottom part also. So pressure is equals to rho g m by r cube, and I'm substituting the value of rho into mass divided by 4 by 3 pi r cube into r square by 2 minus r square by 2, because I don't like the term of density. M and m would become m square. Okay, let's make this neat. Okay, these three would go up. So this 3 is going up. Okay, fair and fine. Now r cube and r cube will become r to the power 6. Okay, r cube and r cube would become r to the power 6. Fair and fine. Now one more thing. Can I take this 2 common out here? Obviously, I can take this 2 common out here. So if I take this 2 common, this 2 and this 2 will come outside. Okay, this 2 and this 2 came outside. 4 into 2 is nothing but 8. 4 into 2 is nothing but 8. Okay, now what I obtained was, let me write this neatly. Pressure is equals to 3 by 8 g m square, 3 by 8 by g m square divided by r to the power 6 into capital R square minus small r square. If I want to make this more neat and clean, take r square common. Okay, P is equals to 3 by 8 by g m square by r to the power 6 r square into 1 minus r square by r square. Okay, so this r square and this r to the power 6 will get cancelled to become r to the power 4. So our obtained is nothing but r to the power 4. Okay, this was the end of question 216. Now to understand this question, okay, you have to understand something called potential of formation. So what is potential of formation? Okay, suppose I have mass m1, m2, m3, m4, and so on. Okay, suppose I have these 4 masses. Okay, these 4 masses are arranged in this way. The question is, what is the potential energy for the formation of this system? Okay, what is the potential energy required to form this system, or what is the work done by gravitational force, or what is the work done against gravitational force in forming this system? Okay, so how do I find out potential of formation? It is nothing but I take mass m1. Okay, mass m1. Now this mass m1 can move anywhere in space. Okay, this mass m1 was kept out here, or was brought out here. Okay, now I have taken this mass m2. Okay, let's take this mass m2, the same mass m2. Now this mass was initially at infinity. Okay, I'm bringing this mass m2 at this position, okay, so that mass m1 and m2 are separated by this much position. Understood? So what is the potential energy out here, or what is the potential energy required, or what is the potential energy formed? Work done by gravitational force is nothing but g m1 m2 divided by r12. R12 is nothing but this distance. R12 this is nothing but r12. Okay, so in order to bring the first mass from infinity, there is no work required, because there is no other mass, isn't it? There is no any other mass that is forming the work out here. Okay, to bring the second mass from infinity to this point, the work done is nothing but g m1 m2 divided by r12, or work done by gravitational force is nothing but g m1 m2 divided by r12. R12 is nothing but this distance. Suppose I bring the third mass, okay, this m3. I'm bringing this m3 from infinity to this point, okay, this point out here, My question is, what is the work done? This is work done in bringing mass 2. Work done in bringing mass 3 is nothing but g m1 m3 divided by R13, isn't it? This much distance plus G M2 M3 divided by R23. R23 is nothing but this much distance, isn't it? R23. So when I bring the third mass, the potential energy of the system would be nothing but work done on this one plus work done on this one. So when I'm bringing the third mass, the work done by gravitational force to bring only this mass is nothing but entire this one. Okay, this is the work done to bring mass number 3. Similarly, if there is fourth mass, okay, M4, and I'm bringing this mass from infinity to this point, what is the work done? Work done is nothing but, or work done by gravitational force is nothing but G M1 M4 by R14, isn't it? R14 is nothing but this distance, R14, plus G M2 M4 by R24. R24 is nothing but this distance, R24. Okay, this distance is nothing but R24, R24. Okay, plus G M3 M4 divided by R34 plus G M4. Acha, first, second, third. It is already done. Okay, so work done to bring the fourth mass. Fourth mass. So if you check carefully out here, the first mass can move freely around in space. There is no work done. To bring the second mass at this specific point, work done by gravitational force is nothing but G M1 M2 by R12. Okay, work done by third mass or work done by gravitational force on the third mass to bring at this position is nothing but G M1 M3 or M1 M3 divided by R13 plus G M2 M3 divided by R23. Similarly, work done by gravitational force to bring the fourth mass is nothing but G M1 M4 plus G M2 M4 plus G M3 M4 and so on. Okay. So to bring any other additional particle, I have to find out the potential energy to bring all the remaining particles. Okay, or potential energy of all the particles. What I'm trying to say is, suppose I bring a fifth particle. Okay, the work done by gravitational force to bring a fifth particle is nothing but G15, G25, G35, G45. Okay, understood? So this is the potential energy of formation. So the potential energy or the total potential energy of the system is nothing but summation of all this potential energy. Total potential energy of the system. Total potential energy of the system is nothing but summation of all this potential energy. This one, this terms plus these two terms plus these three terms is equals to 2 plus 3 plus 4. Work done in mass, work done by gravitational force to bring mass 2, work done by gravitational force to bring mass 3, work done by gravitational force to bring mass 4. Okay. And where is mass 1? What is the work done in bringing mass 1? See, when mass 1 arrived, there was no any other mass in the vicinity, or there was no any other mass nearby. So there was no gravitational force on mass M1. So there is no work done on mass M1. But while bringing mass 2, mass 1 M1 was already present. So this work was done. While bringing mass 3, mass 1 and mass 2 was already present. So this was the work done. While bringing mass 4, mass 1, mass 2 and mass 3 was already present. So this was the work done. Similarly, if you bring mass 5, okay, this 4 mass will be present. So work done will be so on. Understood? Now, one more thing that I have to discuss out here is this is the potential, or this is the potential energy of the system, or potential energy required. Okay, that means what? The total energy, okay, required to form this system is nothing but this much amount. Fair and fine. Now my question is, what is the total energy required if I want to separate out the system? Suppose I am to, this is already a system. Okay, I have to separate this mass in mass 1, M1 goes to infinity, mass M2 goes to another infinity, mass M3 goes to another infinity, mass M4 goes to another infinity. Suppose this system I want to separate out. What must be the total work that I have to give? That is nothing but this entire thing only, isn't it? So if this much amount of work is done by gravitational forces in forming this system, the same amount of energy, this is the unit of energy, no? The same amount of energy I have to give to the system to separate them back to infinity, isn't it? Understood? As a total energy of the system or potential energy of the system is nothing but minus. This is work done by gravity, and potential energy is nothing but negative of work done by gravitational forces. Okay. So total energy of formation of the system is nothing but this one. Okay. Similarly, total energy required to separate the system back to infinity. System back to infinity is nothing but negative of potential energy of the system. Okay, total energy required is nothing but negative of potential energy of the system. Negative of potential energy of the system. That means what? The amount of energy that I have to give to separate the system back to infinity is nothing but potential energy of the system. And what is potential energy of the system? Work done by bringing or work done by gravity force in bringing this mass together in this configuration. And what is the work done by gravitational force? Work done on M1. Since when M1 arrived, no one was there, so work done on M1 is equal to 0. When M2 arrived, M1 was already there. Work done on M2 is nothing but this value. When M3 arrived, 1 and 2 are already present, so work done on M3 is equals to this much. When M4 arrived, 1, 2, and 3 are already present, so work done on M4 is this much. So total gravitational work done in this system is nothing but this entire values, and the potential energy is nothing but negative of this entire values. Okay, and if I want to separate out this system is already formed. This system is there. Okay, now to separate out this system back to infinity. That means M1 goes to infinity, M2 goes to another infinity, M3 goes to another infinity, M4 goes to another infinity. What must what must be the external energy? That means I have to give the system some energy. Okay, I have to give the system some energy to separate this particle back to infinity. What is the amount of energy that I must give it? The amount of energy is nothing but negative of potential energy of the system. So this was the entire concept of potential of formation. Understood this much? Okay. Now in this question, I have to find out the potential of formation of a spherical shell of mass capital M. Okay, I'm just changing the variable from small m to capital M. You're understanding a bit why. Okay, and a solid sphere of mass capital M. Okay, we have to find out the potential of formation of these two bodies: a spherical shell of mass M and a solid sphere of mass M. So let's start first part A of the question. So suppose I want to form a shell of mass M. Shell means all the mass is situated at the surface of the shell. Okay, there is nothing inside. Inside the shell there is hollow kind of thing. Okay, all the mass is situated at the surface, and the mass of this shell is M. Now to find out the potential of formation, what will I do? I'll first bring a mass M. Okay, suppose I'll first bring a mass M. Okay, I'll bring a mass M from infinity to this point. Okay, incomplete shell. This shell is incomplete. Okay, now to make this incomplete shell, work done is equals to 0, isn't it? Why? Because while I was moving this mass M from infinity to this point, okay, there was no external gravitational field, and if there was no external gravitational field, the work done is equals to 0. Now some of you might have questions, sir, when you bought this mass, okay, no external work, but as soon as you bring this mass, there is some external work. No, there is some external work required. Not required, there is some gravitational work done, isn't it? So what about that? See, while integrating continuous mass, the mathematical approach is this way. Okay, if you bring two discrete mass very close together, the value of potential energy will become infinity because the distance between them will be very small. No, so what you have to do is you have to bring the basic shape. Okay, the basic shape out here is M, or an incomplete sphere or incomplete spherical shell of mass M. And then what you have to do is you have to bring the rest of the mass dm from infinity to the surface of the shell. That means you bought a basic sphere of mass M, and then what you are doing is you are integrating this mass dm to make a complete mass capital M. Understood? Okay, you cannot bring elemental masses for the entire thing. Understood? First bring the basic mass M. Basic mass M should be in the shape of a sphere, isn't it? And then bring the rest of the masses to complete the sphere. Okay, so potential energy. So suppose work done or potential energy to bring this small mass M, okay, only this mass M is nothing but 0, and work done or potential energy to bring this elemental mass to the surface is nothing but minus g m into dm divided by capital R. Why is this capital R? Capital R is nothing but the radius of the shell. Okay, and doesn't matter wherever you bring the mass dm, it will always be at the surface, and the distance from the surface is always r. So dm would be always situated at distance r from the center. So potential energy will always be g m into dm by r for a shell. Now to integrate this thing from 0 till the mass capital M is formed, isn't it? So potential energy is nothing but minus g by r. M dm is nothing but m square by 2, and the limits of integration are from 0 to mass capital M. So potential energy is nothing but minus g m square by 2r. Understood? The second part of the question. The second part of the question is nothing but find the potential energy to bring a solid sphere of mass capital M. Solid sphere means the planet is filled with mass M. Okay. So similarly for this kind of question, okay, the radius of the planet is capital R. We first have to bring a basic mass. Okay. The basic mass out here is nothing but let's say a mass of M or a sphere of mass M. Okay. This is the basic mass. So to move this mass around, we do not need any work or no work is done by gravitational force. Why? Because when the movement of this basic mass is done, there is no external gravitational force, no? Because there is no external gravitational field. There is no any other mass to apply gravitational field on this mass, isn't it? So to move this around, there is no work done or no potential energy, or the potential energy would be zero. Okay, there is no change in potential energy. Fair and fine. Now when I'm bringing elemental mass dm from infinity to this point, I have to integrate this elemental mass out here, no, to make this capital M sphere, isn't it? So how do I integrate this mass dm out here? What we'll do is we'll first form a shell. Okay, first I'll bring a lot of dm mass and form a shell out here. As soon as this shell is formed, then I'll situate the dm mass on top of this, and by forming a lot of shells, what I'll do, I'll create this solid sphere of mass capital M. Understood? That means first I got an elemental mass m, and then I'm getting shells out here and integrating the shells till mass m is being formed. Understood? So potential energy is nothing but minus g elemental mass into dm divided by small r. I might have a question. Sir, in the previous question it was capital R and this capital R was constant, which is nothing but radius of the shell. But why did you use smaller out here? Okay, smaller is nothing but the radius of elemental mass. See, in the previous question, the basic shape was the shell itself. Okay, the basic mass out here in the previous question, which I got, was in the shape of the shell itself, no? And I'm integrating the remaining mass on top of the shell only. So everywhere I bring this dm mass will be at the surface of the shell only, isn't it? However, in the next question, this basic sphere is nothing but a solid sphere. Now the dm mass that I bring, the first batch of dm mass would be integrated at the surface of the shell, okay, at radius r. The second batch of dm mass would be integrated above the first layer of shell, no? See, this is the first layer of shell. This is the first layer of shell. Okay, this is the first layer of shell. Okay, after the first layer of shell is being formed, the second layer of shell would be formed on top of first layer, no? So while forming second layer of shell or forming the outer layer of shell, the radius would change, isn't it? Then the value of r would change because I'm bringing the mass dm mass from infinity to the surface, isn't it? So as I keep on integrating, or as the shells, as the size of the shells become larger and larger, the value of r would become large, or isn't it? The value of r would change. Okay, in the first case, I was bringing all my elemental mass to the surface. In the second case, as I'm integrating the shells, the value of r is increasing. Understood? This is why there is a constant r, and out here I'm using variable. Okay, and now I have to integrate this mass from 0 to capital M. Okay, but instead of using that method, okay, I'll use density. And why am I using density? Because in the first case, the radius out here was constant, but in the second case, the radius out here is variable. See, so in order to mitigate this, what I'll do is I'll convert the mass in terms of radius. How? See, can I say the density of planet is equal to density of this elemental shape and density of elemental mass, isn't it? Density of the planet is equal to density of basic shapes, which is equal to density of elemental mass. So the density of planet is equal to density of elemental shape is equal to density of elemental mass, isn't it? So can I say density is equal to mass by volume? Okay. So density is equal to mass by volume is equal to mass by volume of this elemental sphere. Okay. So density is equal to mass by volume. Okay. So let's see what I'm doing out here. This mass m and radius r is the basic shape. And after the basic shape is got, I'm integrating layers of dm shell on top of each other. Understood? Layers of dm shell on top of each other. And then by integrating a lot of shells, I'll get the capital mass m. Okay. So out here, mass of the basic shape divided by volume of the basic shape. Density of this elemental shape is nothing but mass of the element shape divided by volume of the elementary shape. 4 by 3 pi r cube or small r cube. This is nothing but the volume of the elemental shape. Volume of the total planet is nothing but 4 by 3 pi capital R cube. 4 by 3 pi capital R cube. Isn't it? Okay. Mass of, or what is the density of this elemental shell? This dm out here. this dm out here that is being formed, or the elemental shell that is being formed, dm out here. Okay, dm. What is the volume of this elemental shell? What is the volume of this elemental shell? The volume of this elemental shell is nothing but surface area into thickness, isn't it? So the density of this elemental shell is nothing but mass of this elemental shell divided by volume of the shell, and volume of the shell is nothing but surface area 4 pi r square, which is nothing but surface area of the shell into thickness of the shell. Thickness of the shell is nothing but dr, isn't it? Understood this much? Okay, this much is understood. Density of the planet is equals to density of the elemental body is equals to density of the shell. Okay, mass divided by volume, mass divided by volume, dm divided by volume of the shell. Okay, I just have to substitute the value of m out here and dm out here. Understood? Substitute the value of m out here and dm out here. Fair and fine. Now see, from this equation I'll get that potential energy is equals to minus g. What is the value of m? Value of m is nothing but density into 4 by 3 pi r cube. Density into 4 by 3 pi r cube. And the value of dm is nothing but density into 4 pi r square dr. Density into 4 pi r square dr divided by r, because divided by r was out here. Okay, now let's just simplify this one. Rho and rho would become rho square. Fair and fine. Pi and pi would become pi square. Okay, r cube r square, r to the power 5 divided by r to the power 4. Let's make it neat and clean. Rho square. Acha. Okay, r to the power 4. So let's write r to the power 4 out here. Okay, 4 and 4 will become 16. 4 and 4 will become 16. Okay, let's write 4 and 4. Okay, and these 3 is down out here. So potential energy, this is separate. Okay, so potential energy is nothing but minus rho square pi square by 3 into r to the power 4 into dr. There is 16 also. So 16 by 3. Okay, into r to the power 4 dr. And you have to integrate this r to the power 4 from 0 to capital R. You have to integrate for the entire solid state, no? So from 0 to capital R. So if I calculate this one, or when I calculate this one, what will happen is, see, potential energy is equals to minus 16 by 3. Let's see what is it. Rho square pi square 16 by 3, or rho square pi square into rho square pi square into r to the power 4 dr from 0 to r. So it will become potential energy is equals to minus 16 by 3 rho square pi square into r to the power 5 divided by 5. The limits of integration are from 0 to r. So potential energy is equals to minus 16 by 3 rho square pi square into r to the power 5 by 5, isn't it? Now suppose this is the answer. Now suppose this is the answer. Now suppose I want the answer in terms of mass. What do? I'll just substitute the terms of mass out here. And how do I do that? By using the same equation. Okay, we know that density is equals to mass by volume. So mass is equals to density into 4 by 3 pi r cube. See out here. Mass is equals to, or mass of the planet is equals to density into 4 by 3 pi r cube. So we know that mass is equals to density into 4 by 3 pi capital R cube. Okay, so density is equals to mass by 4 by 3 pi r cube. We do not need to use this. We already know that density is equals to 4 by 3 mass by 4 by 3 pi r cube. Okay, so m by 4 by 3 pi r cube whole square. This is nothing but m square divided by 16 by 9 pi square r to the power 6. Now when I substitute this value out here, what do I get? Potential energy is equals to minus 16 by 3 into rho square. M square 16 by 9 pi square r to the power 6 into pi square r to the power 5 by 5. So pi square will get cancelled. 16 and 16 will get cancelled. This 9 will go upward. 3 and 3 will become 9. Let's make this neat and clean. Let's write this 3 down out here. Yeah. 69 got cancelled. Pi square got cancelled. Acha. R to the power 5 and r to the power 6 will become r. Okay. So we get something in the range of potential energy is equals to minus 3 by 5 m square by r. So this is the potential of formation of a solid sphere of mass capital. Understood? So this is the question.